Hello students, welcome back to the classroom point. In our today's class, we shall discuss the equilibrium constant and how to use the calculations based on the equilibrium constant. So let's begin the class now. Now let us try to see the equilibrium constant and its characteristics first. So what is the meaning of the equilibrium constant? Let us take a general equation. AA plus BB is equilibrium with C moles of C and D moles of D. So in our previous class, we have discussed the law of mass action and how to apply the law of mass action to the equilibrium process. That I am taking now. Here, equilibrium constant Kc is equals to concentration of C power C, D power D divided by concentration of A power A and concentration of B power B. So equilibrium constant in terms of the concentration can be defined as it is the ratio between the product of the molar concentration of the products, product of the molar concentration of the reactants whose stoichiometric coefficients raised to their respective powers. Here square bracket represents the concentration. Now the question is on what conditions the equilibrium constant depends. So which factors will influence the equilibrium constant? So you must remember that equilibrium constant K equilibrium depends only on temperature. Depends only on temperature. Other factors like concentration, catalyst do not change the value of the equilibrium constant. So that K equilibrium do not depend on the initial or final concentration of either reactants or products. Because in any equilibrium reaction, you can take any amount of the reactants or products. Equilibrium constant don't depend on the concentration of either reactants or products, because equilibrium constant is always a ratio. If you take the higher concentration of the reactants, obviously they will produce the more concentration of the products, so ratio remains same. So that is the reason why equilibrium constant do not depend on the initial or final concentration of any of the reacting species involved in the chemical equilibrium. Now the fourth factor is catalyst do not change the value of equilibrium constant. So what could be the reason? Because any particular catalyst, if you take for a reversible reaction, catalyst increase the rate of forward reaction and backward reactions with equal rates, with equal magnitude. So in such cases, when rate of forward reaction, rate of backward reaction rate becomes equal, automatically it comes to the equilibrium at the faster rate, but there is no change in the position of the equilibrium or the value of the equilibrium constant. So catalyst helps to attain the equilibrium quickly, but it will not change both the position and the value of the equilibrium constant. Next, let us see the uses of the equilibrium constant. Higher the value of equilibrium constant, more stable the product. And lower the value of equilibrium constant, more stable the reactant. So let us take an example here. Example is, example 1. Imagine A2O molecule is there. It dissociates to give the A2 plus half O2. Imagine all are in the gaseous state. And B2O dissociates into B2 plus half O2. Again in the gaseous state. Let it be this is the first equilibrium constant whose value is 10 power 12. Second equilibrium constant 10 power 15 is there. The question is about in which of the following equations the stability of the oxide is more. Stability of the oxide means you must remember that oxides are on the reactant side. So here reactant, here both are the oxides. That means reactant stability they are asking. Reactant stability depends on lower the value of equilibrium constant, more stable the reactant. So here, which one is having the lower value? This one is having the lower value. That means A2O is more stable than the B2O. So this is the answer for the reaction. Next, let us take A plus B giving X moles of A and Y moles of B gives AX plus BY. K1 value is equals to 10 power 31. Next, A moles of P, B moles of Q reacts with each other to produce PA QB. K2 equals to 10 power 25. So, in which of the following equilibrium reactions the stability of the product is more? Again, we have to go for this particular point. Higher the value of equilibrium constant, more stable the product. So, product between these two, where the K value is higher, in this case, 10 power 31 is there. That means AXBY is more stable than the PAQB. So, this is the answer for the question. Now, let us see the other factors. If equilibrium constant Kc is more than 10 power 3, that means products predominate. Than reactants. That meaning is reaction almost go for completion. So let us discuss this particular point. See why products are dominating than the reactant molecules. Reason is if you see the equilibrium constant formula, products by reactants are there. Higher the value of the products, higher will be the equilibrium constant. So, higher the equilibrium constant meaning is more products are present in this particular reaction mixture. That means reactants almost converted into the products, but still only less amount of the reactants are remain in the equilibrium mixture. Now, let me this is the one. If equilibrium constant less than 10 power minus 3, so that here reaction occurs rarely. And reactants predominate the products. So this 10 power minus 3 means very less value. Less value in the sense here reactant denominator value is higher than the numerator value. That's why total value decrease. That's why Kc value is also less. So automatically we can say that more amount of the reactants are present than the products. So that reactants don't want to convert into the products. So reaction occurs very rarely. Next condition is if equilibrium constant is in between 10 power 3 to 10 power minus 3. So considerable value of concentration of both reactants and products are present. So if the equilibrium constant value is in between these two values, then automatically we can say that the equilibrium mixture is having the sufficient amount of both reactant molecules and product molecules. It is completely in the equilibrium stage. So for any chemical reactions, equilibrium constant can be represented mainly in the three forms. They are Kc, Kp and Kx. So Kc means equilibrium constant is represented in terms of concentration. If only concentration terms are used, then for such type of reactions, equilibrium constant is represented as Kc. So for concentration purpose, we use the square bracket. That means it is a concentration. Kp. So here, the reactant molecules and product molecules of the equilibrium reaction are represented in terms of the partial pressure. So here it is in terms of partial pressure. So for partial pressure, we use the symbol P. And for this one, here the concentrations are partial pressure we don't use, but we represent the both reactant molecules and product molecules in the equation in terms of the mole fraction. That means for that we use the mole fraction symbol Chi, that is CHI. Let us take some general equations and try to apply all these three. As usual, let us take preparation of ammonia by Haber's process. To NH3. So for this reaction, Kc, in terms of Kc means only we have to use square bracket. That means concentration of the product square divided by concentration of the reactants. N2 H2 power 3. In terms of the Kp, so Kp means partial pressure. P has to be used. So partial pressure of ammonia NH3 square, here we are using the normal parenthesis, not the square, and partial pressure of N2 into partial pressure of H2 whole power 3. And in terms of the mole fraction, that is Kx. So mole fraction symbol has to be used. Mole fraction of ammonia NH3 square divided by mole fraction of nitrogen into mole fraction of hydrogen power 3. Like this we can use it. Let us take another equation. Ammonium hydrogen sulfide, solid state. So that here ammonia in gaseous state plus H2S also in the gaseous state. Now for this let us apply it. Solids not applicable. So that for this Kc is equals to concentration of ammonia into concentration of H2S. Similarly, Kp, partial pressure of ammonia into partial pressure of H2S. Kx, that is mole fraction of ammonia into mole fraction of H2S. Like this, we can write down the various equilibrium constants for a given chemical equation. Now let us try to see how these equilibrium constants are related one to another. So first one here, let us see relation between Kp and Kc. So let us recollect the information from the ideal gas equation. We know that what is ideal gas equation? From ideal gas equation, we can write down that PV equals to nRT, P equals to N by V RT. N by V stands for the number of moles per volume in liters, means it's nothing but concentration. So here I can write down that P equals to CRT. P stands for the partial pressure is equals to concentration into R into T. So let us try to take a general equation here. That is, A moles of A reacts with B moles of B, giving C moles of C plus D moles of D. For this, let us try to derive the equation, the relation between the Kp and Kc. So we know that Kc has to be written like this: concentration of C power C, concentration of D power D divided by A power A into B power B. Similarly, Kp means partial pressure of C power C, partial pressure of D power D divided by partial pressure of A power A, partial pressure of the B power B. Now let us try to get the relation here. In the place of partial pressures, I can write down the concentration into R into T, so that the equation now becomes Kp is equals to this Pc I am writing as concentration of C power C into RT power C into, because in the place of partial pressure I can write down concentration into R into T. Partial pressure power the C means in the place of P I can write down the CRT. C means concentration of C. So concentration of the C power C into RT power C power RT power C. Similarly in the place of the D, concentration of D power D into RT power small d divided by concentration of A power A into RT power small a into concentration of B power B into RT power B. Now let us try to write down the, try to separate the equal symbol values to one side, so that we'll get here Kp is equals to concentration of C power C, concentration of D power D, concentration of A power A, concentration of B power B into, here base is same, so that you can sum the powers, RT power C plus D divided by RT power A plus B. Now take this RT to the numerator. Then it becomes Kp equals to, in this place I can write down the Kc, this one, so that Kp equals to Kc into RT power. After taking this one, it becomes the minus value. So C plus D minus A plus B. So what is the meaning of C plus D and A plus B? See, C plus D in this equation, C small d represents number of moles of the products, A and B represent the number of moles of the reactant molecules. That means number of moles of the product, total number of moles of products minus total number of moles of the reactants. But already we have discussed that for solids and liquids, this concentration to be taken as 1 or unity, so that we can convert this particular form as C plus D as number of moles of gaseous products minus number of moles of the gaseous reactants. So now here we can write down that Kp equals to Kc into RT power number of moles of gaseous product minus total number of moles of the gaseous reactants, so that Kp is equals to Kc into RT power delta N. So this is the relation between the Kp and Kc. Now let us see, by changing the value of delta N, how to get the relation between the Kp and Kc. So we know that now the relation is Kp equals to Kc into RT power delta N. So how these are related? Let us take, if delta N value greater than 0, meaning is delta N value if it is positive. So this is a positive value, means Kp becomes equals to Kc when Kc is multiplied by something value. Otherwise Kc is less than Kp. Simple terms, if you imagine this is Kp value is 8. 8 equals to 4 into 2. Then only 4 is equals to 8. Otherwise 4 is less than the 8. That means Kc is less than the Kp, or else we can write down that Kp is greater than Kc. If delta N is less than 0, that means if it is negative. Negative value means here power minus comes, so automatically that you have to write down. So Kp equals to Kc divided by RT power delta N comes. That means Kc becomes equals to Kp when Kc is divided by something. Simple thing, 4 equals to 8 by 2. So that 8 value is more than the 4. So Kc is more than the Kp. So here I can write down that Kp is less than Kc. Next, if delta N equals to 0, then Kp is equals to Kc. Both are equal. Let us try to complete the units now only. Units of Kp and Kc. Kc units are moles per liter power delta N, or else you can write down that Kc equals to molarity power delta N. Kp equals to atmosphere power delta N, or else you can take even bars also. Power delta N. Now let us try to take some equations and apply these combinations. PCl5 in gaseous state dissociates into PCl3 in gaseous state plus chlorine in gaseous state. Both are in equilibrium states. Then first calculate the delta N value. Delta N means total number of moles of gaseous products minus total number of moles of the gaseous reactants. So here how many gaseous products are there? 1, and here 1. 2 are there total. Reactant only 1 is there. So the value is 1. That means it is a positive value. So if it is a positive value, we know that Kp is greater than the Kc. Then units of Kc, molarity power 1. That means molarity only. Kp units are atmosphere or bar. Equation number 2. Let us take N2 plus 3H2 is equilibrium with 2NH3. Now delta N value, total number of moles of gaseous products 2 are there. Reactants 3 plus 1, 4 are there. Total value equals to minus 2. That means negative value. Negative value means relation is here, it is given already. Kp value less than Kc value, and units of Kc, molarity power minus 2, or else we can write down that 1 by molarity square Kc, whereas Kp units are atmosphere power minus 2, or else Kp equals to 1 upon atmosphere whole square. Let us take another equation here. H2 plus I2 equilibrium with to HI, gaseous state. Now here, delta N value, total number of moles of gaseous products 2, reactants also 2. 2 minus 2 equals to 0. That means Kp value is equals to Kc value and no units for both Kp and Kc. Because power value becomes 0 here. Something to the power of 0 is equals to 1. And let's take the final equation. Calcium carbonate solid dissociates into calcium oxide plus carbon dioxide. So here delta N value, solid cancel out, only 1 is there. So 1 minus this side nothing is there means 0. That means 1. Again this is the positive value. That means again Kp value is greater than the Kc value. So like this, if you want to calculate the units of Kp or Kc, or if you want to relate the Kp and Kc, first you need to calculate the delta N value, then we can get these values. Now let us see the relation between the Kp and Kx, that is equilibrium constant in terms of the mole fraction. Kp and Kx. So we know that partial pressure of any compound is equals to total pressure into mole fraction of that compound. So this formula, using this formula, we are going to apply it. Capital P stands for the total pressure, Pa stands for the partial pressure of A, Xa stands for the mole fraction of A. Now let us take the general equation regularly, like earlier also. It gives C moles of C and D moles of D. For this Kp is equals to partial pressure of C power C, partial pressure of D power D divided by partial pressure of A power A into partial pressure of B power B. Now let us take the Kx value. So here we take the mole fractions. Mole fraction of C power C, mole fraction of D power D, divided by mole fraction of A power A and mole fraction of B power B. Now here it is given that partial pressure is equals to total pressure into mole fraction. That means in the place of partial pressures, we can write down the total pressure into mole fraction. So these are the partial pressures. Now we can write down the total pressure into mole fractions. So let us try to change this equation as Kp equals to partial pressure of C means total pressure into mole fraction. Mole fraction of C power C into total pressure P power C into mole fraction of D power D into total pressure P power D divided by mole fraction of A power A into total pressure P power A into mole fraction of B power B into total pressure P power B. So write down the mole fractions first and pressures on other side. So we'll get mole fraction of C power C into mole fraction of D power D divided by mole fraction of A power A into mole fraction of B power B into, here base is same, so you can sum the powers. Total pressure P power C plus D divided by here also P, total pressure P power A plus B. Now you take this P to the numerator and in this place we can write down the Kx. So that here the equation becomes now Kp equals to Kx into P power C plus D minus A plus B. C plus D means number of moles of gaseous products. A plus B means number of moles of gaseous reactants. So that here we can write down that Kp equals to Kx into P power number of moles of gaseous products minus number of moles of gaseous reactants. So that here we can write down that Kp equals to Kx into P power delta N. Again, similar conditions are applicable here. If delta n value is greater than 0 or delta n value is positive, if it is positive, then Kp is greater than Kx. If delta n value less than 0 or negative, it is negative means it comes to the numerator, so that it has to divide the Kx value, then Kx value is more than the Kp, that means Kp is less than the Kx. Similar context we have already discussed in the relation between the Kp and Kc. So similar way here also we are getting the answers now. If delta n value equals to 0, then Kp equals to Kx. So like this, we can derive the equation that relates the Kp and Kx value. Now, let us try to see how to get the equilibrium constants if the reaction is reversed, multiplied or divided. So we can write down it as an applications or uses. So I'll take an equation here. First equation, A is equilibrium with B. For this, write down the equilibrium constant K. That is K1 I am taking. So concentration of B divided by concentration of A. Now second is, if an equilibrium reaction is reversed, if you reverse this equilibrium reaction, that means B is equilibrium with A, then what is the new equilibrium constant? K2 equals to concentration of A divided by concentration of B, products by reactants. But how these are related with each other? So here we can write down that K1, K2 is equals to 1 upon K1. 1 upon K1 in this sense, K1 value is nothing but, you can see this, 1 upon K1 value meaning is concentration of B divided by concentration of A. It goes to the numerator and giving the concentration of A here. So concentration of A by concentration of the B means that is K2. So that whenever any equation is reversed, the equilibrium constant also reversed. That's why K2 is equals to 1 upon K1. Let us take an example here. For the following reaction, N2 plus 3H2 equilibrium with 2NH3, K1 is given as some 40 value is given. What is K for the reaction 2NH3 is equilibrium with N2 plus 3H2. So solution for this. Simple thing is, this reaction is reversed. Let us imagine the next reaction equilibrium constant K2 is equals to 1 upon K1. That means 1 upon 40 is the answer. Now, let us see the third one. If any equilibrium reaction is multiplied by a factor n. So let us take A is equilibrium with B. This is multiplied by a factor n. So the new equilibrium constant is K3 is equals to concentration of B divided by concentration of A whole power n, because both are having the same value. That's why I am taking the whole power n. But how this is related to the first one? See, in the place of this one, concentration of B by concentration of A, I can write down the K1 value. So that K3 is equals to K1 power N. Very simple thing. If any reaction is reversed, the equilibrium constant becomes 1 upon. If any reaction is multiplied, the value goes to the power of that value. If a reaction is reversed and multiplied, then equilibrium constant comes to the denominator, and the value, whatever the multiplication value is there, factor n, that goes to the power. Let us see that example also here. Fourth example. Imagine now I am taking the B with A. Now it is multiplied. Let it be equilibrium constant K4. It is concentration of A divided by concentration of the B whole power n. That means K4 is equals to, these are related. It is the inverse of this one. So you take this value down. So here you can write down it is inversed and power n. What if any reaction is not only multiplied but divided? See here, I am taking the A is equilibrium with B divided by the factor n. Remember that divided is in the sense 1 by n, but we can consider this one as a multiplied by 1 by n, divided by n, multiplied by 1 by n. So that new equilibrium constant K5 is equals to concentration of B power B divided by concentration of A whole power 1 by n. So here I can write down that K5 is nothing but K1 whole power 1 by n. See, if n value is equals to 2, then it is equals to root K1. If n value equals to 3, then it becomes 3 root of K1. If it is reversed and divided, then let us take here sixth one. B is equilibrium with A divided by factor n. So K6. So whenever divided, reversed means first of all it becomes 1 upon, multiplied by 1 by n, or divided, so it becomes power 1 by n. So like this we can relate it, and we shall see some examples also of discussing the equilibrium constant for the multi-step reactions. If a reaction, that means let us take equilibrium reaction or reversible reaction, takes place in more than one step, then the overall constant, that means rate constant, equilibrium constant, the overall equilibrium constant is the product of all the constants involved. Let us take an example. A is equilibrium with B. For this reaction, equilibrium constant is K1. B is equilibrium with C. Constant is K2. C is equilibrium with D. Constant is K3. Then what is the constant value for A to D? That means overall they are asking. So for this, K is equals to K1 into K2 into K3. If these values are given separately, for example 2 is given and 4 is given, some 5 is given, then substitute those values. 2 into 4 into 5. So this is equals 20 into 2, 40. So like this, overall equilibrium constant can be calculated. Now let us try to see some examples. So the given question is like this. K1 is given. They are asking what is the K2 value. If you clearly observe these two reactions, this reaction remains as it is, reactants and products. Only difference between this one is this reaction is multiplied by the factor 2. So that here new equilibrium constant K2 is equals to K1 power 2 because it is multiplied. Simply we can get the relation like this. So the given equation is like this. For this reaction we have to calculate the Kc value and the given data is from this one. So let us try to see here. Kc value I have to calculate here. Kc is equals to, in this equation NOBr is on the right side. Here also NOBr on the right side with the same number of moles. That means Kc is equals to K2. You write down first. Next here, second data given here is N2 plus O2 is on the product side. Here N2 and O2 on the reactant side. That means this reaction is reversed here. So that divided by, this is K1. So whenever the equation is reversed, power divided by 1. And here required equation is having the 1 by 2. That means it is divided. It is not divided. So that this power, whatever 1 by 2 is there, it becomes the power of this K1. Then Kc is equals to K2 value 4 divided by K1 value 4 into 10 power 30 whole power half. That means we can write down this one as 4 divided by 2 into 10 power 15 whole square. Square root cancel out. So 2 into 10 power 15. It goes here 2 times. So that here Kc is equals to 2 into 10 power minus 15. Dear students, I hope you understand my class. If you really understand my classes, please do like my videos and share with your friends, and don't forget to subscribe the channel. We shall meet in the next class. Thank you one and all.